Hey y'all, welcome back. Today we are converting polar equations to rectangular form and vice versa, and also looks like we're going to do a little bit of graphing here too. So before we get into all this, let me go ahead and write down the four conversion equations that we are going to use here. So the first one will be relating theta with x and r. So let me go ahead and throw that in here. So cosine of theta will be x over r. Similarly, sine of theta will be y over r. Tangent of theta will be y over x. Finally, r squared will be x squared plus y squared. So these are pretty much all the equations we're going to use here. Just kind of get these out of the way. Okay. So looking at number one, what we want to try to do is we want to try to maneuver our equations around so that we can use these conversion equations to get it into rectangular form. So like notice on this case, I've got r equals 4 over cosine theta. So I've got r and theta. So I'm going to be looking at some options here to convert. I'm sorry, we've got r and cosine theta. So if I'm looking at these equations, it looks like this is going to be the one I want to use. So for instance, if I multiply both sides by r, I get r cosine theta equals 4. Now this equation over here, this cosine theta equals x over r, can be rearranged, right? If I multiply r on both sides, what I get is r cosine theta equals x, right? So that's exactly what I have here. I get r cosine theta equals x, so now I can make that direct conversion, and I get x equals 4. So just to give you an idea of what this graph is going to look like, whenever you have x or y equals a number, you're going to get just a horizontal or vertical line. If it's a x equals, you'll get a vertical line. So like 1, 2, 3, 4, we'll get a vertical line right there. Now it's not asking you to actually graph this, but I just want you to have an idea of what this graph would actually look like so that when we get down here, it'll go a little bit more smoothly. Okay, so that's number one. Number two looks like, let's see what we got here. We've got 7 tangent theta times secant theta. Looks like we're going to have to use one of our Pythagorean identities here. And we're going to rewrite secant of theta as 1 over cosine theta so that we can move it over to the left-hand side, and then we'll get our r cosine theta that we can rewrite as x. Tangent of theta can be converted directly to just y equals x. So that should take care of all of our polar variables. Remember, the whole kind of goal here is to get rid of r and theta and replace it with x's and y's. So first things first, I'm going to rewrite this equation using 1 over cosine theta rather than secant theta. So if I multiply this by 1 over cosine theta, what I could do is actually multiply both sides by cosine theta, and that will result in r cosine theta equals 7 times tangent theta. Now we've got expressions that we can translate directly. So like r cosine theta, we said was x. Tangent theta is y over x. So we can replace both of those right away. So we get r cosine theta is x times 7 times y over x. Now generally when we're converting to rectangular form, if possible, we want to try to solve for y here. Just so we get an equation that's a little bit more familiar. So I'm going to divide by 7 and multiply by x. So multiplying by x would give me x squared. and then dividing by 7 would be like 1/7 equals y. And so just kind of rewriting this as a y equals equations, we get y equals 1/7 x squared. So this is going to be a parabola, right? Like I'm just going to do a real quick sketch here, but just to kind of remind you, it'll look like that. So there's number 2. Number 3 is a little trickier. What we have to do here, the trick here is we want to take the tangent of both sides. So we get tangent of theta, which is something that we can convert, and we get tangent of pi over 4, which is something that we can evaluate. So tangent of theta is just going to be y over x. Tangent of pi over 4, so let me bring up the unit circle just so to kind of remind you. We're looking at pi over 4, and tangent is going to be the y divided by the x. So that would be root 2 over 2 divided by root 2 over 2, so that's just going to be 1. So this ends up being just y equals x. Now this should match up or just kind of make sense with what the equation in polar form was. So if you know what y equals x looks like, it's just a line with a y-intercept of 0 and a slope of 1. It's just basically this diagonal line. It's a parent linear function. And if you think about what this equation up here means in polar form, let's get rid of that unit circle. Theta equals pi over 4. Well, pi over 4 is right here, right? It should be that 45-degree marker, right? So it does make sense that this equation and this equation would be the same. One thing to keep in mind here is that the graph of pi equals, or theta equals pi over 4 does go in both directions. It doesn't just go in the direction of pi over 4 because we have to consider the fact that there are negative r values, which would be sort of away from pi over 4. So yeah, when we get to the graphing, we'll probably talk about that a little bit more. Yeah, so down here we're converting from rectangular to polar form. So for this first one, we are just going to do a direct conversion here. Let me borrow my conversion equations so I don't have to keep scrolling up. Bring them down here. So you can take a look at them. So we said that x is r cosine theta, right? Similarly, if we solve this next equation for y and multiply both sides by r, we'll get y equals r sine theta. So I can rewrite y as r sine theta, and I can rewrite x as r cosine theta. So just like that, we've got rid of all the x's and y's, and now we've got nothing but r's and thetas. So the only challenge here now is going to be to try to isolate r, which is going to take a little bit of algebra, but it's not too bad. The first thing we want to do is we want to subtract this term, this 3r cosine theta, from both sides to effectively move it to the left side of the equation. So we get r sine theta minus 3r cosine theta equals -2. Now how this is going to help us isolate r is now on the left-hand side, we've got an r in both of these terms, so we can factor it out as a greatest common factor, a GCF, and be left with sine theta minus 3 cosine theta on the inside of those parentheses. Okay, so we've got this expression times r. If we're trying to isolate r, we just need to divide both sides by this entire thing. So we'll get r equals -2 divided by that expression. Probably don't need those extra parentheses, but there you go. So we've solved for r. So like when you're solving equations, when you're trying to rewrite polar equations in rectangular form, generally speaking, you're trying to isolate y. Now in some cases that's not possible, right? Like, on this one up here, we see that there's not even a y to isolate. So in that case, you just isolate x. In some cases, it's not going to be possible to isolate y or x, but if you can, you try to go for y. Now, if we're going from rectangular to polar form, same kind of rule applies here, except instead of solving for y, you want to try to solve for r. Generally, these equations, if we're going to write them as functions of theta are going to be r equals equations, if possible. There are some cases where you cannot, or if you end up like an equation like this, then you just solve for theta if there is no r. So let's take a look at number 5. We're going to take a similar strategy here where we rewrite. So actually, no, number 5, we're not going to use these two formulas actually at all. Now I'm looking at this a little closer. What we want to do is we want to square both sides so that we can actually use that last conversion equation. All right? That way I've got the x squared, y squared. I'm hoping that it can kind of turn into this. So let's see what's going to happen here. We've got x squared equals, now when I square root, those effectively cancel each other out, so I just get 2 minus y squared. If I bring the y squared over by adding y squared to both sides, I get x squared plus y squared equals 2. And so now I can use this conversion, right? So this is just going to be r squared. Oh, what the? Let's try that again. R squared equals 2. And so if I'm trying to solve for r, I'll get r equals the square root of 2. Algebraically, there probably should be a plus minus there. But if we're going to graph this, the graph of r equals root 2 is going to look equivalent to the graph of r equals negative root 2. So you don't really need to graph both of them. They're both going to be circles centered at the origin with a radius of root 2. In other words, like, they're going to be a circle where the radius is root 2 all the way around. But we'll get to the graphing later. For number 6, we want to use those first couple conversion equations and rewrite it as r sine theta equals 3. This one's pretty straightforward. You're just going to divide both sides by sine, and you'll get r equals 3 over sine theta. Now this is probably a good answer. You can take this a step further because 1 over sine theta is cosecant theta. So if you rewrite it like this, that's acceptable too. Honestly, I'll take either one, but I do want you to know that these two are the same. They are equivalent. So this is, like, if it's a multiple choice question, this is probably going to be the option I'm going to go with. But if it's a free response, like, this is an acceptable answer. This is good too. So that's how we go from polar equations to rectangular form and vice versa. So now let's take a look at the graphing. I'm going to bring these conversion equations down just in case we need them. I might just reference them. I don't know if we're actually going to need them or not, but it couldn't hurt. You know what? It's going to make me copy and paste it. That's okay. Let's just bring these back up to the top here. Okay. So number 13. All right, for number 13, we get r equals 3. This one, there's not a whole lot to say about this one. It's just a circle with a radius of 3 centered at the origin. So if I count 1, 2, 3, trying to square that up, should be able to kind of get that pretty close there. It's not going to be perfect, but it should. Oh well, I think we can do better than that. There we go, that's pretty good. Okay, yeah, there you go. I mean, there's not really a lot to say about it. If you wanted to see what it would be like as a rectangular equation, you could square both sides and get r squared equals 9. And then r squared is x squared plus y squared. And so you would have the equation for a circle has a radius of 3. Okay, this number right here is the radius squared. So yeah, that's just what it would be. For number 14, we get theta equals negative pi over 3. So here we want to locate where negative pi over 3 is. So here's where positive pi over 3 is. Right, so negative, instead of rotating in a counterclockwise direction, we are going to rotate in a clockwise direction. So like here is negative pi over 3. But when we draw the line, we want to make sure it goes in both directions because we may have negative r values. In other words, the coordinates over here could be something like negative 1 comma negative pi over 3, or negative 2 comma negative pi over 3. So the theta value is still negative pi over 3, so this equation is satisfied, but with the negative r values, we do get the complete line. If you're curious what the rectangular equation would be, we would get there by taking the tangent of both sides, and then we would evaluate. So tangent of negative pi over 3 would be like that. Oops. Nope. Let's try that again. 3. This tangent of theta would be y over x, and which I'm getting from over here, and then tangent of negative pi over 3. If we bring up our unit circle, we could see negative pi over 3 is coterminal of 5 pi over 3. And so we'd have the y over x, which would be this negative root 3 over 2 over 1/2. So it would just be negative root 3 over 1, so just negative root 3. And then if I multiply both sides by x, I get this linear equation that has a y-intercept of 0, and it has a slope of negative root 3. So this is like a y equals mx plus b style equation. Now it's not asking me to convert these, but I just figure it doesn't hurt to kind of see a few more worked out. We don't have to do it for everyone, but anyway, so there you go. There's 13 and 14. So for number 15, we have r equals secant theta. Now it doesn't really look like immediately we can use any of these equations, but if we rewrite secant theta as 1 over cosine theta, we can multiply both sides of the equation by cosine theta, and then we've got the r cosine theta that we need to convert. So r cosine theta is just x, all right? So this is x equals 1. So in this case, it's probably easier to actually convert to know what it looks like. If you have something simple like r equals a number or theta equals a number, those are just going to be a circle or a line. But if it's secant or cosecant, you're probably better off converting it first, so that I think most of us will know what x equals 1 looks like before we know what r equals secant theta does. So this should just be a vertical line where x is 1. I'm trying my best to make that vertical. And there you go, there's your equation, or there's your graph. 16 will be solved similarly. We'll rewrite cosecant as 1 over sine, so we get r equals 3 divided by sine theta. All right, so I multiply both sides by sine theta. Which is y, according to our conversion equations up here. R sine theta is y. So y equals 3 is going to be a horizontal line where that goes through the y-intercept of 3. 1, 2, 3. That doesn't really look too horizontal. I'm trying to make that a little better here. All right, well, I'm probably just overthinking it. Yeah, so you get a horizontal line there. Now 16 through 18 are in rectangular form. Number 16 we can convert pretty easily. It's going to be r squared equals 4. Although you may already know what this is going to look like because x squared plus y squared equals 4 is in a common format. It's just going to be a circle. But we can see if we convert it into polar form, it'll be a little bit more obvious what it should be. R is going to be 2. Square root of 4 is 2. So what we'll have is a circle at 2. So let's see, 1, 2. Oops, wrong shape. 1, 2. Okay, 1, 2. All right, number 17. You probably don't need to convert this one, quite honestly. If you know that this is just a line that has a y-intercept of 0 and a slope of -1, you should know that it's just going to do something like this, okay? You don't need to convert it, but if you did convert it by dividing both sides by x and then rewriting, y over x as tangent theta, you could say tangent theta equals -1. And then if we were going to solve for theta, we would take the inverse theta of both sides. I'm sorry, inverse tangent of both sides. So we get theta equals the inverse tangent of -1, which is going to be, strictly it would be negative pi over 4, but yeah, it would be negative pi over 4. You don't really need to do that though, if you know what this is, if you know what this line looks like. So anyway, so the last one, really there's no reason at all, again, to convert it. This is just a parabola, it's just your parent quadratic function. So you've got points at 0, 0, 1 squared is 1. So what I'm kind of imagining here is like a grid, like an overlaid grid on here. So if I have a point at 1, 1, you know, here's the x where x is 1, right? Here's where the y is 1, roughly. So 1, 1 would be like right here, okay? Roughly. And then -1, 1 would be roughly right here. 2 squared is 4, so I go over 2 up 4, and I'm looking here, let's see, 1, 2, 3, 4. So 2, 4 is going to be like right over here somewhere. -2, 4, same thing. So we get this nice little parabola going. And that's pretty much it. You don't need to convert this. You could, I guess, just for fun, we might as well just go ahead and do it since we did all the other ones. You get r sine theta, which is y, equals r squared cosine squared. Just to kind of clarify this, really it's r cosine and then the whole thing is squared, but when you square a product, really you're just squaring each individual factor. So we'll get r, would basically get what I had written before, which is r squared, there we go, times cosine squared. Now, there's a little bit more that goes on to this, but basically we would want to solve for r. We don't need to do that because we already know what this graph looks like. Let's see, this one's going to be a little trickier. Yeah, this is going to require a few more steps. That's not really necessary. I don't think it's really worth going over. But basically, that's kind of where you'd go. I'm not going to ask you to convert something like that. So anyway, that's it for today. Y'all have a great day.